A deep dive into ECC. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are taking a comprehensive deep dive into the reigning champion of modern public key cryptography, Elliptic Curve Cryptography, or ECC. We will move beyond a simple overview and explore the history, the core mathematical concepts made easy, and the practical, real-world applications and security considerations of ECC. By the end, you will understand why this elegant technology is the engine behind the security of your mobile phone, your web browsing, and the entire world of cryptocurrency. The pioneers of ECC. The story of ECC begins in 1985 when it was independently proposed by two mathematicians, Neil Koblitz and Victor S. Miller. They recognized that the mathematical properties of elliptic curves could be used to create a trapdoor function, just like RSA, but with the potential for much greater efficiency. For years, their idea was primarily of academic interest. It wasn't until the late 90s and early 2000s, as the need for stronger and more lightweight cryptography grew, that the industry began to take notice. Today, their invention is one of the most widely deployed cryptographic algorithms in the world. The limits of RSA. To understand why ECC was so revolutionary, we need to look at the limitations of its predecessor, RSA. RSA's security relies on the difficulty of factoring large numbers. As computers get faster, following Moore's law, the size of the numbers we can factor increases. This means that to keep our data secure, RSA key sizes have had to grow exponentially. A 1024-bit key, considered strong in the early 2000s, is now considered weak. Today, we need 2048 or even 3072-bit keys. This trend is unsustainable, especially for small, low-powered devices. The world needed a new algorithm that didn't have this baggage. What is an elliptic curve? So what exactly is an elliptic curve? For our purposes, it is a specific type of curve defined by the equation you see here. The exact formula is not the important part. What is crucial is that these curves possess a unique and consistent set of rules for adding points together. This is not the addition you learned in school. It is a geometric operation. This special property, that we can define a predictable way to combine points on the curve to get another point on the curve, is the entire foundation of ECC. The real world. Curves over finite fields. Now, here's a key detail. We don't actually use the smooth, continuous curves you see in textbooks. Computers can't work with infinite precision. Instead, we use elliptic curves that are defined over a finite field. This means the x and y coordinates can only be integers within a specific range, determined by a large prime number. The result is something that looks more like a scattered, symmetrical pattern of dots than a continuous line. But even though it looks different, the amazing thing is that all the mathematical rules for point addition still work perfectly. All the geometry we discussed now happens using modular arithmetic. Visualizing point addition. Let's visualize the special addition rule. To add two different points, P and Q, you draw a straight line through them. This line is guaranteed to intersect the curve at exactly one other point. We'll call this point -r. You then reflect this point across the x-axis to find your final result, r. So, P plus Q equals r. There's also a rule for adding a point to itself, called point doubling. To do this, you draw the tangent line to the curve at point P. This line will also intersect the curve at one other point. You reflect that point across the x-axis, and the result is P plus P, or 2P. By repeating these simple geometric operations, we can perform complex calculations. The generator and subgroups. When we choose a starting point on our curve, the generator G, it has a special property. If you start adding G to itself, you generate a sequence of new points, G, 2G, 3G, and so on. Eventually, this sequence will repeat, and the set of all unique points you can generate from G is called a cyclic subgroup. The total number of points in this subgroup is called its order. The domain parameters for ECC are carefully chosen so that this subgroup is very large, and the generator G is a point that can generate the entire group. This ensures our keys have the largest possible space to exist in, maximizing security. The rules of the game. Domain parameters. Before any ECC can happen, all parties must first agree on a set of rules, called the domain parameters. Think of this as choosing the specific game board and pieces everyone will use. This ensures that everyone's keys and calculations are compatible. These parameters are public and standardized. They include the specific elliptic curve equation, the prime number p that defines our finite field, and most importantly, the generator point G. Every calculation starts from this same G. Some famous sets of these parameters include sec P256K1, used by Bitcoin, and curve 25519, which is popular in TLS. The trapdoor. Elliptic curve discrete logarithm problem. This brings us to the core of ECC's security, the trapdoor function. As we've established, if we take our generator G and a secret number D, it's very easy to perform point multiplication to find the final point Q, but reversing this is what's known as the elliptic curve discrete logarithm problem, or ECDLP. Given G and Q, find D. This is believed to be a much harder problem than factoring large numbers. There is no known shortcut algorithm to solve it efficiently on a classical computer. This massive gap in difficulty, easy to go forward, impossible to go back, is the perfect foundation for a strong cryptographic system. Generating your ECC key pair. The process of creating your own public and private key is now very straightforward. First, you select a standard set of domain parameters, like curve 25519. Then, to create your key pair, you just need to do two things. First, you invent your secret. You generate a very large, cryptographically random number. This number is your private key, D. Second, you perform the point multiplication. You calculate the result of adding the standard generator point G to itself D times. The resulting point on the curve, Q, is your public key. You can share your public key Q with anyone, but as long as you keep D secret, no one can reverse the process to figure out your private key. What a real key looks like. Theory is great, but what do these keys actually look like in practice? On this slide, we're using the common OpenSSL command line tool to generate a new ECC private key. This command creates a file containing not just the private key itself, but also the domain parameters, so the software knows which curve is being used. When we inspect the file, we see the private key is just a very large number, shown here in hexadecimal. The public key is derived from it and is composed of the x and y coordinates of the final point on the curve. This is what's actually exchanged during a secure handshake. ECC versus RSA, the efficiency battle. So why go through all this trouble with curves and points? The answer is incredible efficiency. The mathematical problem that ECC is based on is believed to be much harder than the problem of factoring large numbers that RSA relies on. Because the problem is harder, we can use much smaller numbers and still get the same level of security. As you can see from the chart, a 256-bit ECC key, which is common today, provides the same security as a 3072-bit RSA key. This isn't just a small improvement, it's a massive difference. Smaller keys mean faster calculations, lower power consumption, and less data to transmit during a handshake, all of which are critically important for the modern internet. Key exchange with ECDH. Now let's look at the primary application of ECC, agreeing on a shared secret key. This is done with a protocol called Elliptic Curve Diffie-Hellman, or ECDH. Its purpose is to allow two parties who know nothing about each other to establish a shared secret over a completely public, insecure channel. It is not an encryption algorithm itself, it is a key agreement protocol. The shared secret they generate can then be used to derive one or more symmetric keys for a fast cipher, like AES or CHA-20, which will handle the actual encryption of data. Detailed example. ECDH key exchange. Step 1. Let's walk through a detailed, simplified example of elliptic curve Diffie-Hellman, or ECDH first. Alice and Bob agree on the public domain parameters. A curve and a generator point G next. They each create their own secret. Alice generates her private key, a random number, let's say it's A equals 5. Bob generates his private key, let's say it's B equals 12. These are their ultimate secrets and are never shared. Their goal is to use these secrets and the public parameters to independently arrive at the same shared secret number that an eavesdropper cannot figure out. ECDH example. Step 2. Public key exchange. Now, Alice and Bob each compute their public key by multiplying their private key with the generator point G. Alice computes her public key A by adding G to itself 5 times. So, A equals 5 times G. Bob computes his public key B by adding G to itself 12 times. So B equals 12 times G. Remember, these results A and B are points on the curve, not numbers. They then exchange these public keys over the insecure network. An eavesdropper, Eve, can see G, A, and B, but she cannot figure out Alice's secret 5 or Bob's secret 12 because of the ECDLP trapdoor. ECDH example. Step 3. The shared secret. This is the final, brilliant step. Alice takes Bob's public key B and multiplies it by her own private key A. Her calculation is S equals 5 times B since B is just 12 times G. Her calculation is really S equals 5 times the quantity 12 times G, which equals 60 times G. Meanwhile, Bob takes Alice's public key A and multiplies it by his private key B. His calculation is S equals 12 times A since A is just 5 times G. His calculation is really S equals 12 times the quantity 5 times G, which also equals 60 times G. They have both independently calculated the exact same final point on the curve, 60 times G. This point is their shared secret. They can now use the coordinates of this point to derive a symmetric key for fast encryption. The man-in-the-middle problem. But there's a catch with the ECDH protocol we just described. While Eve the eavesdropper can't figure out the secret, what if she is a more active attacker? She could intercept Alice's public key and send her own public key to Bob instead. Then she could intercept Bob's key and send a different key to Alice. Now Alice and Bob would unknowingly establish separate secure channels with Eve in the middle, who could then read, modify, and relay all their messages. This is the man-in-the-middle attack. ECDH by itself does not provide authentication. To solve this, we need a way to prove who we are talking to. We need digital signatures. Application 2. Digital signatures with ECDSA. The other major use case for ECC is providing proof of authenticity and integrity through digital signatures. The algorithm for this is the elliptic curve digital signature algorithm, or ECDSA. A digital signature provides 3 crucial security properties. First, authenticity. It proves who created the signature. Second, integrity. It proves the data has not been altered since it was signed. And third, non-repudiation. The signer cannot later deny that they signed the message. This is the technology that secures software downloads, legal documents, and cryptocurrency transactions. Detailed example. ECDSA signature. Now let's look at a digital signature with ECDSA. Suppose Alice wants to send a signed message, pay Bob $10. First, she calculates a cryptographic hash of this message to create a short, unique fingerprint. Let's call this hash Z. Next, she generates a new, secret random number just for this signature, called K. This number is a nonce and must be unique and unpredictable. She then uses her private key D, the message hash Z, and this random number K as inputs to the ECDSA signing algorithm. The output is a pair of numbers, R and S, which together form the digital signature. She sends the original message and the signature R and S to Bob. ECDSA example. Step 2: the verification. Bob now needs to verify that the message truly came from Alice. He has the original message, the signature R, S, and he knows Alice's public key, Q. First, Bob calculates his own hash of the message he received. If it doesn't match the original hash value embedded in the signature, the verification fails immediately. If it does, he proceeds. He uses Alice's public key Q, the message hash Z, and the signature components R, S as inputs to the ECDSA verification algorithm. This algorithm will only return true if the signature R, S could have been created by the private key that corresponds to the public key Q. If it returns true, Bob has mathematical proof that Alice, and only Alice, signed that exact message. The danger of nonce reuse in ECDSA. There is a catastrophic mistake a developer can make when implementing ECDSA: reusing the secret random number K. This number is also a nonce and must be unique for every signature created with the same private key. If Alice signs two different messages using the same private key and the same value of K, an attacker who sees both signatures can perform some simple algebra to completely recover her private key. This is not a theoretical attack. This exact vulnerability was used to hack the Sony PlayStation 3, allowing users to sign their own custom software. It's a powerful reminder of how important correct implementation is in cryptography. So, how do you encrypt with ECC? A common point of confusion is that we've discussed key exchange and digital signatures, but not direct encryption. That's because ECC itself is not an encryption algorithm. To actually encrypt a message for someone using ECC, we use a hybrid scheme that combines these primitives. The most common standard for this is the Elliptic Curve Integrated Encryption Scheme, or ECIES. It combines an ECDH key exchange with a symmetric encryption algorithm and AMAC in short. To send an encrypted message, you generate a temporary, one-time ECC key pair. Use ECDH to create a shared secret with the recipient's public key, and then use that secret to encrypt the message with a cipher like AES-GCM. The world of curves. Not all elliptic curves are created equal. Different curves have different properties that make them better for certain uses. The most common type are Weierstrass curves, like the NIST standardized P256 or SEC P256K1 used by Bitcoin. These are well understood but can be tricky to implement securely. More modern applications have shifted towards newer types of curves, like Edwards curves and Montgomery curves. A famous example is curve 25519, which was designed by Daniel Bernstein. These curves are specifically engineered to be not only fast but also much more resistant to implementation errors and side-channel attacks, making them a safer choice for modern software. Practical application. The TLS 1.3 handshake. Let's see how this all comes together in a real-world protocol, like the TLS 1.3 handshake, which secures your web browsing. When your browser connects to a server, it generates a temporary, one-time ECC key pair for this session, and sends the public part to the server. The server does the same. They both perform an ECDH key exchange to establish a shared secret. But how do you know you are talking to the real server and not a man in the middle? The server also has a long-term identity certificate containing its public key, which it uses to create an ECDSA digital signature over the entire handshake. Your browser verifies this signature, authenticating the server. This combination of ECDH for secrecy and ECDSA for authenticity creates a secure channel. Practical application. Cryptocurrency. ECC is central to how most cryptocurrencies, like Bitcoin, work. When you create a Bitcoin wallet, you are essentially generating an ECC private key. Your public key is then used to derive your public wallet address, which you share with others to receive funds. To spend your Bitcoin, You create a transaction message and then use your private key to create an ECDSA signature for that transaction. This signature proves to the entire network that you, as the owner of the private key, authorize this payment. The security of the entire Bitcoin network relies on the strength of the ECDSA algorithm and the assumption that no one can guess your private key. Where is ECC used today? Because of its strength and efficiency, ECC is everywhere in the modern digital world. It is a cornerstone of the TLS 1.2 and 1.3 standards that provide the S in HTTPS, securing your web browsing. It is used by secure messaging apps like Signal and WhatsApp to provide end-to-end encryption. It is the algorithm used to secure transactions in nearly all major cryptocurrencies, including Bitcoin and Ethereum. It is also used for securing remote connections via SSH and for digitally signing software to prove its authenticity. If a modern application needs public key cryptography, the chances are extremely high that it is using ECC. Strengths of ECC. Let's summarize the key strengths of elliptic curve cryptography. Its most significant advantage is efficiency. It provides the same level of security as RSA with much smaller keys, leading to faster computations, lower bandwidth usage, and less power consumption. This makes it ideal for everything from massive web servers to tiny IoT devices. It is also built on a well-studied mathematical problem, and after decades of analysis, it is considered to have very strong security. Finally, its versatility in enabling both key exchange and digital signatures makes it a complete toolkit for building modern secure systems. Weaknesses and considerations. However, ECC is not without its weaknesses and challenges. Its mathematical concepts are far more complex to understand than RSA's, which can make it feel like a black box to many developers. This complexity also means there are more opportunities for subtle implementation mistakes, like the nonce reuse vulnerability, which can have catastrophic consequences. The choice of curve and its parameters is also critical, and there have been debates in the community about the trustworthiness of some standardized curves. And finally, like all mainstream public key algorithms today, its security would be completely broken by a sufficiently powerful quantum computer. The quantum threat. Like all public key cryptosystems currently in use, ECC is not invincible forever. A sufficiently powerful quantum computer running an algorithm called Shor's algorithm would be able to break ECC by solving the elliptic curve discrete logarithm problem. While such a computer does not exist yet, this future threat is taken very seriously by cryptographers. This is why there is a major ongoing effort, led by institutions like NIST, to develop and standardize a new generation of post-quantum or quantum-resistant public key algorithms that are not vulnerable to this kind of attack. The transition to these new algorithms will be one of the biggest challenges in cryptography over the next decade. Conclusion. Faster, lighter, stronger. Elliptic curve cryptography represents a massive leap forward in the field of public key cryptography. By building its security on a harder mathematical problem, it allows us to achieve the same level of trust as older systems like RSA but with significantly smaller keys. This efficiency has made it the indispensable engine of modern digital security, powering everything from our web browsers to our blockchains. While we must look ahead to the post-quantum future, for now, ECC remains the undisputed king of the asymmetric world. Final thoughts. We've covered a tremendous amount of ground today, from the basic geometry of curves to the practical details of key exchange and the looming threat of quantum computing. The key takeaway is that ECC's superior efficiency has made it the cryptographic workhorse of our time. Understanding its principles is crucial for anyone building secure systems today. The field of cryptography is always evolving, and the transition to post-quantum standards will be the next great chapter in this story. Thank you for your attendance. Please consider subscribing to the channel.